Hi, hello everyone. Okay, I'm going to admit I didn't sleep enough and I'm a bit nervous, so please take that into account. Thank you. Yeah. Welcome to my talk, Scaling Alps from HPC to Apertus. My name is Nina Mujkanovic and I work for CSCS as a machine learning engineer. I have a pretty long background in HPC. I started working as a sysadmin while I was studying at university, and that kind of was the entry drug, and one thing led to another, and I ended up working first for Cray and then for HP when we were bought. And since I did machine learning at university, I thought, I want to do more of this, so I decided to go for a job at CSCS, and that's how I ended up here. So this talk is going to be structured into 3 sections. I'm calling them the past, the present, and the future. CSCS probably wouldn't, so please excuse me. And I just wanted to kind of give a future outlook, structure it better for you so you have an idea of where we are going in a way. So I'm going to start with our background, which is obviously HPC. Then there's going to be a long section about Apertus, which I guess people are looking forward to. And then I'm going to end it on Alps, which, you'll get to know what it is. So who are we? We are the Swiss Supercomputing Centre and a unit of the Swiss Federal Institute of Technology, so the ETH. We were founded in 1991 in Mano in Ticino, and we moved to Lugano in 2012, so that's also where a big flagship system sits. A bit of our history, this is taken from our website, the beginnings. So around 1980, the Swiss Federal Council or the Swiss Federation decided, look, things are going on, there's a Cold War, we don't have enough computer scientists, so we should do something and improve the situation. And they said they want to invest into this big system and wind up engineering within the country. And in 1985, they decided, let's do it. And they gave a 6-year deadline to have the entire thing established, the first system set up. The deadline was the 30th of September, 1991. So, of course, on the 30th of September, 1991, we opened our doors. CSCS today has about 127 staff members, plus additional interns and so on, 25 nationalities, and we actually speak English as an official language, although if you go to Lugano, it's all Italian. Our building is fairly large, 2,600 square meters of offices, again in Lugano, and we have a 2,000 square meter machine room. Our yearly budget is 30 million for the operational side and 20 million for IT investments. And on the electrical power side today, our system Alps uses 11 megawatt. We can possibly extend it to 25 megawatt, and all of this is 100% green energy as it's hydroelectrical. And here an internal thing. I wanted to give you a scale, and since this doesn't scale well to bananas or to football fields, you get a train. So the Torino train at 100 meters uses about 6 megawatts of energy, or at a 200 meter length, so the one you have going from Zurich to Bern, you're using 12 megawatts. So we're in that ballpark approximately with our energy use. We are very well tied in with national and international collaborations. So Meteo Swiss calculates its weather forecasts on our systems, has been doing so for a long time. We collaborate with PSI. We have been collaborating with the SKA and CTA projects, collaborations with CERN, and of course we have a lot of research output. On the bottom right you see Lumi. We also collaborate with the Lumi people in Finland, where we also have parts of one of the partitions that we access. Our research infrastructure is called Alps. You've probably already heard about it, and within Alps it's not just the hardware itself, it's an entire platform where we develop and operate a high-performance computing and data research infrastructure to support world-class science in Switzerland. That's our goal. And this is the Alps research infrastructure, which I'm going to talk about. But first, why are we doing supercomputing? So why am I standing here talking about this? Why is this even a thing? Predicting the weather. So weather is chaos. Initially, people did not predict the weather, obviously. They thought it was God-given. And there were natural phenomena. You could look at bullfrogs, you could look at different animals and so on and tell what the weather is going to be like. And this is a quote by me and probably the Victorians. I'll get into this, maybe. So the Met Office in the UK was established during the Victorian era, and it was used for maritime meteorology. So again, a connection to the military, but also to the economy. And in 1854, they basically established the first data collection systems, the first production of weather charts. They founded the actual entire science of weather forecasting and this concept of synoptic meteorology. So the global weather basically is tied together. You cannot have weather in one location in Zurich without having a certain type of weather in London. It shifts, it influences each other. This whole development was aided by the new electrical telegraph to be able to send data faster. And the first storm warnings were issued in 1860. At one point in 1861, they were able to issue forecasts even 2 days ahead. So that was really good. But the publication ceased in 1866 because, quite frankly, they were correct about 50% of the time. And if the fishers went out to sea because they trusted the weather was going to be good and there was a storm, they were not happy. On that note, the admiral actually, he was shunned for a long time after this because while the Victorians believed themselves to be scientific and going beyond God and doing these things that are possible, he was ridiculed for a long time and ended up committing suicide at some point. Going further beyond this, in the weather forecasting by numerical process, Lewis Fry Richardson in 1922 actually defined the mathematical equations that describe atmospheric flow and that divide this entire equation across the globe into cells. So these are actually the formulas that are still used for weather calculation today. And I really like this image. It's not from Richardson's book itself, but an artist rendered it years later. But in the book, Richardson wrote, if you have a myriad of computers being people in this case, so what we would call accountants today, and if all of these computers work upon the entire weather with each accountant sitting on one part of the map, and if this work is then coordinated by an official of higher rank across the regions, then you can calculate this global weather tied to the regional weather, so the synoptic concept. And I really appreciate this image because this is basically what we do with MPI. You have a master rank that coordinates all of the tasks, all of the processes. And if you have 64,000 ranks across an entire system, this is how you can actually compute the weather. Of course, sorry, wrong slide. So Meteoswiss, as I mentioned already, computes the forecast at CSCS, and this is a very long-standing collaboration and has also seen some updates until 2024. They used the Cosmo model, which used rectangles to simulate basically the Earth, the region. And since 24, they use Icon. So this is really an updated version that uses icosahedrals. So all of these triangles that you see across the region, it maps much better to mountains and improves forecasting in mountainous areas. HPC, of course, goes beyond the weather. We have a lot of chemistry and materials, physics, life sciences, computer science itself, nowadays also ML. All of this requires compute infrastructure, and here you see the first mainframe that was actually built in Switzerland. It was built at the ETH between 1956 and 58 and was used until 1963. And as a side note, again, going back to the weather, this will be kind of a theme during the presentation. The first successful computer-assisted weather forecast was done on the ENIAC in 1950. We at CSCS have, of course, tried to keep up to date with the current happenings with the infrastructure. In 1991, the first system was the 5.5 gigaflop Adula. And our newest system nowadays is the Cray EX Alps, which is a pre-exascale system. And what I like in this image is actually you can really see the timeline of how we went from these very unique, very purpose-built systems to commodity hardware that we use today. So these older systems are architecturally and visually very interesting, and nowadays racks are standardized, blades are standardized, and you basically can just exchange GPU, CPU, all of the components, and slap on some really nice images. We have pioneered accelerated computing and cloud-native HPC in Europe. We were not the first to use GPUs in HPC. That would be Titan in at Oak Ridge in the US in 2008. But in Europe, we were among the first, or the first, to deploy GPUs in a supercomputer in 2011. Pitstein, the previous system in 2013, was the first hybrid petascale supercomputer that used GPUs. And it was also the first system to have GPU-based weather predictions in 2015. Pitstein was again extended in 2017. At that point was Europe's largest and the world's greenest supercomputer. And we were at that time NVIDIA's launch customers for the P100. Our latest system is competing with other systems for the position of the largest and greenest supercomputer in Europe. So Lumi kind of grabbed the rank recently, but this depends on the benchmark. And we are contenders to Europe's most capable OpenAI supercomputer, where we also compete with Lumi and Jupyter in Germany. And with Alps, we were again NVIDIA's launch customer for the GH200, so for the Grace Hopper superchip, and have seen really, really tight collaboration with NVIDIA to get everything working, to get bugs removed, and I will mention more about this later. So the Alps research infrastructure itself is a heterogeneous supercomputer. It's HP Cray technology. It uses the HP Cray Shasta slingshot network, their cabinets, their power distribution, their cooling. And the system itself is somewhat geo-distributed. So physically, it's in Lugano at CSCS, but there are also other components on other systems, such as at the EPFL, at the PSI in Villingen for the data archives. And there are some outliers in Bologna for ECMWF for our collaboration with them. The Alps compute composes of about 2,688 nodes times 4 GPUs. So you get 10,752 Grace Hopper superchips with a total memory across all of the chips of 6.9 petabyte ROM. And here you can see an NVIDIA image of the conceptualized superchip. We have the hot storage, fast flash, and a large disk. So we have a performance scratch that's 100 petabytes over 8,480 HDD. We have capacity scratch, which is faster, so 3.2 petabyte over SSDs. And the newest storage that we have is for services. So it's 1 petabyte of a vast data platform for the home directories and 10 petabytes of a vast scratch for data management. All of this, again, is networked via Slingshot. So we have 25 gigabyte per second low latency Slingshot. And this is just the topology that it uses, which is a Dragonfly topology. Makes for a 3-layered connection. You have the edges, you have the local groups, and then you have the global interconnection between all of the groups and nodes. The core kind of piece of the system, or the driver, the most efficient part of it, are the Alps Grace Hopper. And the question is, what does this change for us? So here you see an actual compute blade opened with the 4 Grace Hopper chips. So each module has a 288 core Grace CPU and 1 H100 GPU. And the power limit is about 624 watts. The GPU and the CPU, they share the power budget, but the CPU has precedence in any case. And the interesting thing here is you have the unified address space. So within a module between the CPU and GPU, you can access all of the memory available, and this across, again, all 4 modules in the node. This ends up being 128 gigabytes of CPU and 96 gigabytes of GPU of unified address space. So one process can potentially have 896 gigabytes of memory in one node. And below you just see a list of the different speeds, CPU to CPU, Grace to Grace with NVLink. And the important thing here is, again, we can treat the entire space, the CPU and the GPU memory, as one big transparent space that can help without rewriting the code. And on the right, you see the HPE and NVIDIA and our concept or mapping of how all of this is interconnected. Infrastructure is key for modern AI developments. So I think everybody here knows that deep learning or machine learning in this direction of neural networks really exploded in 2011 when Krzyzewski basically said, okay, let's put all of this in GPUs. All of the codes existed since the 80s, the 90s. You had MNIST and so on, but it only really took off once you had the computational power to train a model quickly. And what this means for us is on the left, you have a table that shows how your validation loss while training an LLM improves as you increase the compute. So that's a very tangible effect. And on the right, you can see the training times and the performance required to achieve a certain training time for different models up to 2024. So, of course, we have newer models now that extends this. But of note here is the line at the top basically shows you what you can achieve with 1 day on Alps if you had the entire system available. If nothing failed, if there were no bugs, if you could fully employ everything, you could train ChatGPT-3 in less than a day using floating point 16 tensor cores. So that's quite good. If you don't have the infrastructure, no modern AI is possible. Accuracy and computational power are really directly related to this. And the rate of increase in flops needed is really staggering because it's just growing much faster than Moore's law did before. Infrastructure, of course, on the one side, but you can't achieve a lot of projects if you don't have the necessary talent to actually implement these things. Like the government decided in 1980, it wants computer scientists. We need ML engineers. And Swiss talent in AI is pretty strong. We have a lot of publications, and the impact of a stronger educational systems, of course, plays into this. So we have the ETHs in Zurich and in Lausanne. EPFL, yes. We have the cantonal universities, and we have the universities of applied sciences. But of course, I'm going to bring a corny joke here. I had to. Just as they say, how many popes do you have per square kilometer? 2.23. You can never outpublish the Vatican. It just pollutes your data. It's, yeah. So once you have the talent and the infrastructure, you got to have a project. So the Swiss AI initiative was established a couple of years ago with the ideas of developing capabilities, know-how, and talent to build trustworthy Gen AI in Switzerland with Swiss values, so sovereignty, and to make these resources available for the benefit of Swiss society and global actors, so openness. And to achieve this, a Swiss AI structure was established with over 70 professors. I know it's about 88 PIs who are working on these projects, specifically Apertus, but also other ones, over 500 PhD and postdocs. It's a huge project between the ETH, EPFL, us, and many other collaborators. And one of the outcomes of this project, as you all know, is Apertus. So I'm just going to go a little bit into this. So this is a bit from a talk from one of my colleagues called Behind the Curtain, Training the 70 Billion Apertus Swiss LM on Alps. So Jonathan presented this last year at the AI and X Summit here in Zurich. And basically, Apertus was released in September 2025. Trained on 15 trillion tokens, and 40% of the data is non-English. So we have over 1,000 languages that Apertus can deal with to varying degrees. There were two models that we trained, a 70 billion parameter model and a smaller 8 billion version. And all of the weights, all of the models, all of the training recipes, the source, everything is open. And to repeat it again, the training set is open. So it's the biggest open LLM in the world. Not saying it's always working the best, but it's definitely sovereign and open. Training such a model requires a lot of time, a lot of engineering, a lot of bug fixing, and a lot of getting hardware to work, especially if you're working with cutting edge hardware that has never been deployed anywhere else. So this is just a timeline of the engineering effort that took over 3 months to be able to scale up and be able to finally train the full model. So you can see that in March, the initial performance reliability was observed and early tests investigated on how to begin. Pre-training began end of March on 2048 GPUs, where we started kind of scaling up. Performance became stable at the end of April. Only in the middle of May did we achieve actual node stability. So I will get into this with the following slides. Things were not easy going at all. At the end of May, we were able to scale the model to double the throughput. And the resources were finally doubled at this point to 4,096 GPUs. And by the end of July, through a lot of tough work involving a lot of people, we finally successfully trained the 15 trillion token model. And the hard deadline was in August. After that, you took all of this, you did the standard training, and you got the Apertus model. Challenges included performance variability, scaling issues, system instability, kernel bugs, driver bugs, network issues, I/O issues, and application issues with Megatron. We had everything fail at some point. And we did succeed. Teamwork makes the dream work. So between Swiss AI collaboration, CSCS, HP, and NVIDIA, who really collaborated very tightly with us on getting the GPUs and everything working, we were able to go from the above training performance, where you see a lot of variability, a lot of drop-off, to basically achieve linear, I can't say the word right now, linear output over time. Workarounds included various things. Here you can see basically the stack that's involved in training Apertus. You start at the bottom of Slingshot, then you have libfabric on top, then the Amazon OFI plugin, which is named a bit unfortunately, but it's very common in the community to use to connect the different components. Running Nickel on top, then PyTorch, Megatron, and finally Apertus. And what we discovered after a lot of debugging was that libfabric doesn't work with all of the AWS OFI versions. This drove one of our engineers crazy for approximately 2 months. So it sounds easy when you see it here. It was not simple to track down why are the containers that we're running failing. Because we do run these workloads in containers. This is part of our cloud native concept that I'll get into later. We had huge performance variability, as you can see in the right graph. This was another issue that took approximately 2 months and ended up involving engineers across different teams, from ML to a storage team to a networking team and so on, just to track it down to an I/O and shared global file system issue. If you have a lot of different users interacting with the same system, you introduce variability. That's just a problem. And that was solved by placing the datasets and the caches on a high IOPS SSD and storing the checkpoints, because they're too large for this, it doesn't make sense, on the HDD, and by setting the optimized striping. We discovered kernel panic issues and system crashes, which was fixed in newer kernel versions. And here's our eternal problem. We cannot really upgrade things on the system. It has to remain stable. This is typical for HPC. We did do a live kernel patch here. But with other things, our workarounds were the GPU driver doesn't work. It doesn't access the counter-based page migration. There is a bug there, and this just causes interrupts on certain CPU cores. So we again had unpredictable performance. There was a fix for it in the next driver. We can't install it yet. We can't upgrade to this. Not possible. So workaround is we just disable the feature. No feature, no problem. We had, this is typical for HPC, I promise. We had problems with the GH200. Its design allows for kernel to use the GPU memory, but there was a bug that basically prevented the migration of certain cache files from the GPU memory back to the CPU memory. At some point, you run out of memory. So this was also fixed in the next driver. We couldn't use it at that time, so the workaround was to really aggressively delete the cache, remove everything before training, and request the kernel to really only allocate tempfs on CPU memory. We had random crashes at basically every Apertus startup. That was basically tracked down to one of the libraries for the NV runtime compiler, which had problems loading the GPU kernels, and the workaround there was to create custom containers that included an updated version of the library, because again, we couldn't install it directly on the system. It was later upgraded to a newer PyTorch version and a newer NGC version where the bug was fixed, so after that, Apertus worked. We did also establish some improvements. We weren't just fixing issues, but also trying to work out how to use things more efficiently. So we were able to enable NVIDIA's vBoost feature, which decreased the chip memory power and increased the GPU clock frequency. And this really improved the compute-bound workloads, and LLM is compute-bound. We disabled the transparent huge pages because these can cause really slow fragmentation routines in the kernel. And again, fixed a new version, not on Alps at that point, turned it off, just kill it. We identified numerous small collective operations that were causing problems with Megatron. So we consolidated that into fewer and larger messages by using the Megatron distributed data parallel bucket size. And while scaling to 4096 GPUs, we had to make 2 modifications to the model parallelism to work this out. So we removed the delayed computation of the embedding gradients. We increased the grad norm. We increased virtual pipelining from 2 to 5 layers, and we had larger throughput at the cost of more communication at this point. I hope that you felt frustrated listening to me. If you didn't understand most of this, that's cool, because that's kind of what it felt like, finding these issues and debugging, and now I have a problem. We don't have a lot of time. So Apertus was really an enormous engineering effort to deliver a stable system and get the entire project to scale. It was a close collaboration between a lot of partners. No turnkey solutions were available, and really deliberate investment was required to make all of this work. Back to the Alps research infrastructure, I said earlier that we are GPU focused, but also cloud focused. So we have vClusters, which are dedicated partitions with tailored software environments. And what this means is that instead of keeping the traditional way that an HPC system works with a fully tightly integrated vertical architecture that cannot be changed, that blocks users from easily installing things that they need, they don't have root permissions, everything's monolithic, there's a vendor lock-in because you have to wait for the vendor to provide things and fix bugs. With Alps, we decided to go in a different direction. And Alps itself sees the resources as independent endpoints that are connected within this high-speed network. And we use this for a tenant-specific and platform-specific service. So aspects of cloud technology are integrated here. And in this case, we're talking about a versatile software-defined cluster that bridges HPC and cloud paradigms, and vServices on top of that, which are really loosely coupled services that are tied to a specific vCluster. This entire approach is three-tiered. You have user environments where users can install what they need themselves on top of the stack via containers or the user environment that we have established on the system. We have service management where you can automate the services. There's some self-healing vetting of nodes. And at the bottom, you have infrastructure as a code, so resource provisioning and the multi-tenancy and labeling. The vCluster provides 10 specific clusters that are shared between the bare metal hardware. Local partitions are defined through code, and I will not go into detail with this because of time issues, and this is not my project. So the Alps platform itself, and this is also why I called the talk Scaling Alps, is split into these vClusters that are logically defined and separated for different customers. You have the HPC user lab, you have climate and weather, which is separate from Meteor Swiss. You have the machine learning, where Swiss AI is housed and Apertus was run, Icon 22 at the top for Meteor Swiss. And all of these are named after different mountain peaks. So Clarendon for Swiss AI, we have Balfrin, we have Dint, and so on. This is why conceptually we call the platform Alps, because we have all of these different peaks or vClusters that can be easily scaled up, changed according to user needs, and are just all a part of this big platform. Beyond this, we have a different concept that we used to deal with sovereign AI initiatives. So you have massive throughput requirements for training foundational models that you just can't deal with traditional HPC architectures. The problem is that subsequent AI life cycles don't fit into what you can achieve with HPC. HPC is usually Slurm-centric, and AI users don't anticipate to work with this. They anticipate one-click solutions. Inference workloads are long-running. They're meant to be highly available services. And we had to deal with the issues of how do you prevent a high-end HPC node from idling during low traffic periods, which you would generate if you were running this inference workload permanently. And finally, how do you balance batch processing with interactive services if you're again running inference? And this is where we introduce Alpanetis, which is a project that kind of plays side by side with the vCluster. So the Apertus offers a hybrid architecture that integrates the diskless nodes that we have in our system with commodity hardware and VMs into one Kubernetes managed control plane. The idea is really at the end to have domain-agnostic self-managed sandboxes so that the users themselves become independent of us, independent of sysadmins, and can install their own applications and move their own projects easily. This entire supercomputing fabric is integrated as a component of a cloud-native orchestration environment, and Slurm operates independently from this Kubernetes environment. The idea is, again, for service-oriented workloads like inference, agentic systems, RAG applications to be orchestrated natively through this Kubernetes. And finally, to just really remove vendor lock-in. So Apertus, in its core, is basically a combination of the vCluster Alps nodes and commodity hardware VMs. At its core, it uses SUSE Rancher, SUSE Virtualization, GitOps, Argo CD, and OpenTofu for the infrastructure, Terragrant at the very bottom. It has different types of node flavors. I will not go through all of them. I have to speed it up. The important point is there's a mix of virtualized nodes, a mix of bare metal nodes, and a hybrid mix. And the point that I really need to drive home, because I was instructed to do this, again, not my project, is that beyond just virtualizing things, beyond staying at that layer, Apertus is actually able to access the nodes bare metal. So if you use it, you can have access bare metal to the local disks, the NICs, the GPUs, and so on. And this is really an important distinction compared to other projects that are trying to do the same thing. And this is a concept of a cluster that you could have using Apertus with the virtualized nodes of Harvester on the left, the vCluster in the middle, on the right, the VMware, and totally on the right, the bare metal nodes. And in this example, you would have 60 different clusters assigned over all of these different nodes and groups. This helps us do different things beyond just Apertus. It helps us, for example, work on trusted research environments, which is one of the currently ongoing new projects that integrates HPC and ML under strict regulations. So it's, for example, HIPAA compliant, which is the US law, or it complies with ISO 27001, which is more local. We at CSCS are trying to build tomorrow. So we have a long history in HPC. We have been serving the AI and ML communities and the AI factories of tomorrow with Swiss AI, with Apertus, with different programs, but we're also developing new ways of melding HPC and cloud to deliver more flexibility, more performance, more science. So we have virtualized or bare metal access with Apertus. And this is the last slide. I just really want to encourage you, since again, the last two, vCluster and Apertus, are not my projects. We have the papers online. You can read the paper about vCluster by Maxime Martinasso et al., the Apertus paper by Dino Canciatore et al., and the last shout out, this was a recent blog article on our homepage. And basically, the Apertus project, you can read at the total bottom, earned the SUSE Virtualization Visionary Award. So we are getting somewhere with our projects. Thank you very much for your attention.
Thank you, Nina.